When you learned a programming language, you likely learned the syntax and the various commands and concepts such as loops, variables, conditional statements, etc. Your programs could be laid out in a simple flowchart, and importantly, they were always in control of when inputs could occur. A simple example is a program and machine for sorting M&M candies. The program is in a constant loop of getting the next piece of candy, recognizing the color, then placing the candy in the appropriate bin. Notice that the input of color was only needed at one point and could be acquired at that instant, assuming a candy was present in front of the sensor. In the same way, many industrial manufacturing processes can be modeled as a repetitive loop where input can be gathered when needed to drive any choices that must be made by the machine's algorithm. But there are many other classes of systems in a wider range of application that cannot be made to work that way. The key issue in these systems is that some external input must be acted upon in a very short period of time, or at the very least must be captured and eventually acted upon, not being missed or dropped. A video game is an example of such a system where the player's input is unpredictable and may consist of several possible inputs. All of the player's input should be captured and the game should respond appropriately. These inputs are a subset of so-called events and suggest an alternate method of programming called event-driven programming. In event-driven programming, the algorithm structure is divided roughly into two groups, events and services. An event is something of importance that occurs, and a service is code that executes as a response to the event. The general approach is to constantly check for events, then execute the associated service routine when so that events are not missed. The service routines should be optimized to operate very quickly. Thus, the program can quickly return to checking for events. It would be wrong to write a service routine that goes into a while loop that can only exit when a particular switch is pressed by the user. This structure is referred to as blocking code and is not compatible with an event-driven structure. The user switch should have been recognized as an event and serviced accordingly. Let's consider a simple example of event-driven operation in everyday life. Imagine starting a coffee maker in the morning, then turning your attention to getting yourself ready for the day. You know the coffee will be done after 5 minutes, so you occasionally check your watch as you brush your teeth and whatever else you need to do. When 5 minutes have elapsed, you pour the coffee, add what you like, and shut off the coffee maker. The event is the point in time when the 5 minutes have elapsed and the service is retrieving and preparing the coffee. Notice that this approach frees you to accomplish other tasks while waiting on the coffee to brew. Events occur when change happens. A switch goes from open to closed, a timer goes from armed to alarm, etc. So event checkers test for the occurrence of an event. They must be coded to remember the past, such as a switch being open, and check the present, such as whether the switch has been closed. An issue with event checking can occur if a mechanical switch triggers an event. Because mechanical switches commonly bounce when changing state, some means of avoiding multiple apparent event triggers must be employed. The solutions most commonly employed are either electronic filtering or an algorithm that ignores apparent switch presses for a short time after the first press is detected. The ignore time should be longer than the expected settling time of the switch. Another common issue with event checking occurs when an analog input is used to trigger an event. Every electronic signal has some amount of inherent noise that causes the analog signal to vary. Imagine a system that must react to pressure in a vessel. Perhaps the system must open a valve when the pressure is above a certain amount, but close the valve when the pressure drops below that same quantity. Since noise will be present on the pressure signal, the threshold value could be crossed several times in a short time period. This effect is similar to a mechanical switch bouncing. Two common methods are frequently used to alleviate this issue. The first is a low-pass filter, either in software or hardware, and the second is hysteresis. One way to employ hysteresis is to use a slightly higher pressure than the threshold to open the valve and a slightly lower one to close the valve. The difference between the higher and lower level should be larger than any reasonably expected noise amplitude. Event-driven programs usually consist of any initializations needed, then operate a continuous loop of checking for and servicing events. The bulk of the programming work is then in organizing the problem to be solved by event-driven code and writing the individual check and service routine pairs. This naturally breaks the programming problem down into smaller, more reasonably sized tasks. But 50% of coding effort is writing and 99% is debugging. But the event-driven approach eases debugging by breaking it into two parts as well. The first part is ensuring that the event service pairs attend to all responsibilities of the program and work well together. The second is debugging of the individual event service pairs.